Hello, everyone. Welcome back to the AAS YouTube channel, and this is the good stuff. This is the AAS Journal Author Series, and I'm very happy to have Gabriela Navarro with us today. Hi, Gabriela.
Hi, Frank. How are you?
I am doing super duper this morning. My morning. What time is it where you're at?
Well, here is 6 p.m. already.
And where is here? What's your geolocation?
Well, I'm in Rome now, in Italy.
Oh, Rome. Okay. Okay.
Yes.
Very cool. Did you have to do a quarantine going in?
Well, not a quarantine, but we are kind of, following some rules and restrictions, but it's fine. We still can come to the university, so we can follow the research anyway.
Very good. Very good. Yeah, we're doing okay on that here. I'm in Phoenix. And there's sort of a mad scramble for everybody trying to get the vaccine going and get that rolling.
Yeah, let's hope the situation gets better with the in the next month. Yes.
But otherwise, it's a, what am I doing today? It's a rare winter day in Phoenix. It's actually fairly cool. It's wet. There's a north wind blowing. So it's a day to
try. Same situation here, I think. Rome is pretty cold in winter, but it's fine. I think we can survive.
Everybody breaks out their winter gear. The slightest hint of coolness in Phoenix, so it's great. Cool. So Gabriela, what do you like to do for research?
So what I'm doing is stellar population. Specifically, I'm doing like two different topics. So I'm doing RLIRAS in the galactic center, let's say the galactic bulge, and I'm studying also microlensing events in the center as well. So all the time, the motivation is more or less the same. So it's studying the structure, the evolution, and even the formation of the Milky Way using especially infrared data. So we can go through the dust in the galactic center and we can detect some objects. So this is more or less my research project now. And this is more or less my PhD thesis, yes.
Cool. So did you finish your PhD thesis?
No, well, I'm almost done with the PhD. So I'm supposed to finish on June, July. So I'm now searching for postdocs and writing the thesis and getting the last results, but it's going pretty well. So yes.
That's awesome. Well, congratulations on being very close to being finished. And I think I will still refer to you as Dr. Navarro.
Thank you. Thank you.
And that is going to take us to this very lovely article, which I think has just a fantastic title. VVV Survey Microlensing, Catalog of the Best and Forsaken Events. And Gabriela, take us away.
Okay, so this is let's say the most important article that we published about the microlensing events that we found with the VVV survey. So I will start talking a little bit about what is a microlensing event, and then I will go through the results of this article. So basically, a microlensing event that is in the introduction, actually just there, is the effect that happens when an object passes near the line of sight between us and a background star. So this will cause a deflection of the space of the space-time, and so of the deflection of the light rays coming from this background star. So this is happening in different scales. In this case, microlensing is in a very short scale. So let's say, for example, the galaxy. So for example, if we're observing a star that is located in the center of our galaxy, and something like an object that in this case we call the lens will pass near this line of sight between this background star and us, will deflect the light rays, and we will see, instead of these multiple images that we expect to see in bigger, in greater scales, we will see an increase in the apparent brightness of this background star. So basically, this is what we are searching for. We are searching for like an apparent increase in the brightness of a star due to a lens that is passing near the line of sight, basically.
Cool. Yep.
So this is very useful to detect many different kind of objects, but especially dark objects, because we don't have to observe or receive light rays coming from these lenses, but we can feel the gravitational force around this object, and we can detect it through this background source. So we can detect from planets to even black holes. And now we are going to talk about this a little bit. So far, the surveys that are discovering these events in the galactic bulge are OGLE, MOA, among others, but these are the most important one. So the interesting thing is that VVV survey is a survey that is observing in the infrared. So we can go through the dust and the gas that is located in the center of our galaxy, and we can go through it and discover stars. So why I think that this is very important, these results, because it's complementing pretty well the optical surveys that are discovering thousands of microlensing events in the galaxy. So if we go a little bit down, we will see, well, this is the introduction that is more or less what I talked about already. And it's talking about the surveys that discover already some events so far. So what I'm going to explain now is what we use. Yeah, they're just a little bit up. So what we use to discover these microlens events, as I mentioned before, we are using VVV data, that is the near-infrared data, and we are using specifically the galactic center, let's say, plus minus 1.5 degrees in latitude and minus plus 10 as it's written there. Yep. Yes, this is the area that we covered in the first stage of our search. And for this, what I try to do is to use the standard microlensing model. That is what you are, that is in the equation 1 and 2. And we can see there that the flags, let's say the brightness that we're going to receive from the star will depend on this amplification factor. Mm-hmm. And this factor will depend on different characteristics of the event itself. So I just want to mention some of the parameters that we are taking into account when we are modeling microlensing events. So the U that you can see there, and if we go to the next formula, we will see it. So the U that is a little bit up, yes. So this is a minimum impact parameter, and this depends on these other parameters that you see there. And the ones that they have a note, they are the maximum or minimum, the maximum moment, let's say when the alignment is the maximum, okay? Mm-hmm. So the important thing here is not just the formula. The important thing for you to understand is that this event depends on the time, on the how aligned they are, and on the masses of these two objects, and finally on the transfer velocities. So these are all the things that we have to take into account if we want to study microlensing events. So what I did, just to start with this searching for microlensing events with the VVV data, we use just the standard microlensing model. That is the one that you are looking at here now in the equation. And this is the basic one. Let's say that the background star is just a star and the lens is another single object. We are not talking about binaries in this time. We are just talking about the simplest kind of configuration that we can have. So what I did is basically use this model to search for all the objects that the VVV was scanning in this area that I mentioned before. There are 10 to the 7 sources, so it's like a very important amount of stars. And I tried to detect this kind of shape in the light curve using a procedure that actually I just created, trying to weigh the different, features that we expect from a microlensing light curve, and then giving like a quality number to these different light curves and trying to just, decide whether this can be a microlensing or another thing, okay? Mm-hmm. So if we continue a little bit down, we will see that I put some constraints a bit down. I think they are just you know, all the explanations. If we go a bit down, you can see there in the table some numbers, but basically it's what I explained already. So I put some constraints on the features that we expect to find. It's just there. So basically, what I was trying to see is to like create in my mind, I try to, you know, to detect these microlensing sources. So for example, one of the things that I was asking to my pipeline to discover is like just a constant baseline, then suddenly like an increase in the brightness of the source, and suddenly a decrease, and then a constant baseline again. So basically that's it. And from this search, we found around 655 events. Actually, this is the number, it's just there. 655 events. And then I took into account the fact that the VVV is observing in a very interesting way. So the VVV is scanning the sky, but it's not just taking one image of each moment that it takes an observation, but it's moving the detector to fill the gaps between them. So in some places, we have an overposition of some very small areas in the sky. So I use that just to check for duplicated events. And indeed, we found some of them. So in some cases, I found, for example, a microlensing event in the edge of the detector. And then I found the same one in the edge of another observation. So then I realized that it was the same. And actually, I mixed the data from both to construct like a more detailed light curve. So this happened, and using this, we recovered some objects, and also we decided that some of them were duplicated. So the final sample is 630 microlensing events. But why we talk about forsaken events? Because there are some events that they didn't fill all the requirements that are pretty strict, I would say, just because I wanted to be sure that the first sample was quite reliable. So there are some events that we didn't include in the final sample, and actually just a bit later, I will show some of the examples. So if we go down, we can see some of the results. This is just a couple of tests, so we are not going to go through the details of these figures. So if we go a little bit down, yes, still we have to, yes. So this is, for example, figure 3 is one of the examples of an event that we didn't include in the final sample, but indeed we can see that it's a clear microlensing event, because you can see the black dots are the data, and the model is the blue and red lines. So you can see here that it's following pretty well the model, but we don't have any data point in the second part of the event. So we cannot constrain the parameters pretty well. So this is why I decided not to include it. You see it?
So you only caught the rise. You don't even necessarily get the peak, and you certainly don't get the fall.
Yeah. So it's not clear, and the most important parameter that we are obtaining from the microlensing event is the time scale. So the time that it takes the whole event to happen, because this is related to the relative distances, the transfer velocity, and the masses. So then we can compute the mass of the lens, that is the goal. So in these cases, it's not clear. So that's why I decided not to include it in the final sample. And we have around 2,000 events that were these second quality ones that we didn't include. So this is one example. That indeed, for example, some other surveys like OGLE, they take them as microlensing events. So that's why sometimes some people get confused, because we expect to find way more events in the galactic center, but I just selected the first quality ones.
Got it. The best. The best.
The best, yeah. For now, at least we selected just the best.
Yep.
So if we continue a little bit down, I talk about the forsaken events. So there were some incomplete light curves, as I mentioned before. If we go a bit down, I will show some of the other kind of forsaken events that I found. So we are talking about very short time scale events or like parallax effect. I will show a bit later, but for now I will talk about this. And what it's important to mention is in the figure 5. So this is important because, okay, so we discovered 630 microlensing events that are the white dots that you see there. This is a color magnitude diagram. And this is very important to detect like different stars of different stellar populations in the galactic bulge. So here you see a Hess diagram of all the stars of the bulge that we analyzed. And in white, you see the 630 microlensing events. We use the color magnitude diagram to select a subsample of stars or sources of these microlensing events that can be located in the red clamp. So these stars are both low mass stars that we expect to find a lot of them in the galactic bulge. So they are very likely to be in the bulge. So this is good because we can kind of guess in distance. So we always use the red clamp sample to study the trends of time scale that I will mention in a bit. But in this case, we use this. So we use the color magnitude diagram. As you can see there, I don't know if it's clear for you, but there is like a line that is moving all the stars towards the red and faint edge, So this line that you see, this, yeah, exactly, is the direction of the extinction, let's say extinction that we can find in the galactic bulge. So in the diagram of colors, let's say, we find a part that is blue, right? This is the densest part. And if we go a little bit up, we see a structure that is like this a bit. And this is the red clamp. Yeah, in this, exactly. This is the red clamp. And we selected all the microlensing events that were falling in this area of the red clamp. And we say, okay, these are red clamp sources. So we know that these sources are located in the bulge, okay?
Yep, I'm with you.
So we will always talk about all the sample, the complete sample, and the red clamp sources, because it's more reliable to study the population of microlensing events of the red clamp sources, okay?
Cool, yep.
So we can go down and we can continue taking the results. So this is the first part of the results. And I just showing how I decided to, to select the red clamp sources. So we can go down still. Yep. So again, here is more clear, right? It's the same color magnitude diagram, but this, the axis, the y-axis is corrected by the extinction. So now the line that you could see like this now is horizontal, and you can see the red clamp selection there. That are the red events, and the white events are the others, let's say.
Yes.
So it's more or less the 50% of the sources are in the red clamp, and the other 50% are in other places of the color magnitude diagram. So this is basically the final sample, the first part of the results. And if we go a little bit down, we can see what else we find. So we can study the spatial distribution of these microlensing events. We can go down still. This is a color diagram. Yeah, we have a lot of figures in this article. So it's nice to see like all the trends. For example, this is a very nice set of figures. So what you see here, basically in the figure 10, is the extinction map of the area that we analyzed that is in red colors, let's say. So the most extincted area is the darkest one, and the less extincted is the lighter. So you can see here that the extinction in the galactic center is really variable and it's really strong. So that's why I think these results are important, because it's the first time we are discovering microlensing events in this area, and we see how difficult it is to detect them and to deal with extinction sometimes. So in the first figure that you see there, there are all the Microlensing events with the squares that are proportional to the time scale. So the nice thing here is that the biggest square are the longest time scales, and we can say that they are probably the most massive lenses. Okay, so what I did here is just to separate between the longest time scales and the shortest time scales, and to see how they are distributed in the galactic center. And basically, I took just the time scale longer than 100 days that we would say that the lenses might be black holes or neutron stars. And you can see that the distribution is they're spread around the galactic plane. Yep. And this is something really interesting now, because I'm really into this, and now I'm dealing with some simulations. And we think that if the galaxy was formed through merger of globular clusters, for example, and there were some stellar mass black holes coming from these clusters, we expect to find a lot of stellar mass black holes exactly in this place, let's say. So this is what I'm searching for now. Actually, this is the place where we expect to find many stellar mass black holes. And the best way now to detect them is Microlensing event. If we can follow them, and with the new telescopes that are coming now, we will be able to detect them. So if we go a little bit down, we will see the short time scale events that they are more concentrated in the galactic center, as you can see there, So these, we can talk about, let's say, very low mass stars or even free floating planets, but I will talk about it a bit later because VVV is not the best discovering planets. So I'm sorry for this, but we are going more for black holes. I will explain why later. So, so this is more or less the distribution of events separated by different time scales. And this is what we found. Of course, all the time, as you can see, they increase towards the center because we have more stars there. So as the density of stars is increasing, the probability to have a Microlensing event is increased as well. Sure. So basically, this is what we see. So if we continue down, we can see more different kind of events. For example, I talk about different kind of events apart from the simple, like the Microlensing light curve that we expect. So this is one example of a binary event, for example. So you see that the baseline is pretty, pretty flat, and then sometimes at some moment it starts to be brighter, but you can see some points there that are very, very bright compared to the other. So probably this is a binary lens. So we see a double event happening at the same time. And then the alignment is pretty good in this very magnified area of the light curve. So this is super nice. Of course, these are the most difficult to model because you have a lot of many more parameters to model, and also because, as you can see, the cadence of VVV is not the best to discover them. But anyway, we have some candidates that probably we will study in detail later. So if we go a little bit down, I talk also about very short timescale events and parallax effect. So here, for example, you can see a very short event. So it's just a spike, that it took like 12 days, because this is half of the time. So the time scale of this event is 12 days. And this is pretty short. And this is a very, very low mass object that was lensing the background star. And the opposite happened in the next figure. So you can see there, this is one of my favorite ones because, so what happened here? So this is a very long time scale event, very, very long. But as you can see, the data is not following very well the feed, and it's quite asymmetric. I don't know if you see at the beginning of the event, you see that there is like a departure from the standard Microlensing model, and this is the parallax. So since the Earth is moving around the sun, the line of sight will change a little bit. So we will see an asymmetry in the light curve due to these very, very long timescale events. So this is good because sometimes you can have a very long timescale event just because the transfer velocities are really low. But in this case, you can kind of say that if you see parallax, you can tell that this is a very massive object. So it's very interesting. I think this is one of the best things that, that the BBB can discover, because we have 5 years of observations and the length of a black hole will be around 1 year. So this is what we are searching for now. So if we continue, we have a lot of very interesting objects, but something that we have to include in the analysis when we want to study the whole microlensing sample, we have to take into account the efficiency. So now we talk about the efficiency a little bit. So there are 2 efficiencies that I took into account to study this. So there is the sampling efficiency and the photometric efficiency. The photometric one is just due to the fact that we detect less stars when we are going to the galactic center because of crowding or because of extinction. This is just one thing that we can study and we include in the final analysis. But also we have to include the sampling efficiency. And this is very, very important when we are studying microlensing events, because when we observe in an irregular pattern, like a regular cadence, we are not going to detect the events all the time, right? It's not like detecting, for example, variable stars. In this case, we are really affected by this. So one example of this is what you see in the figure 17. So you see in the upper panel, you see the number of observations in the 5 years of the VVV. And you see in the lower panel, the number of events, the maximum magnification of the events discovered with the VVV. And they're very similar. So this is very surprising because we are really affected by the sampling efficiency in this case. And why we are observing in this like a very, concentrated moments of the year is because the bulge is visible in winter from Paranal Observatory. So we cannot observe all the time, the same amount of time. So this is something that we have to take into account if we want to study the whole population of microlensing events, because we have a bias due to the sampling. Yep. So what I did is to study the sampling efficiency, creating using Monte Carlo simulation to create fake microlensing events with different time scales, with different time of maximum magnification, and try to recover them using the observations of the VVV. So the result is a little bit down. So the results were what we expected, basically. That is, of course, this is another example of what we were talking about just before. So a little bit down, we will see the results. These are just examples. Still.
21?
Yeah, the next one. I think it's the image 22, if I'm not wrong. Yes, that one. So in figure 22, we can see the result of this efficiency analysis that I was talking about. So here what we see, so the different colors are the different tiles, let's say the different areas that the BBB was observing. And we see in the x-axis the Einstein ring crossing time or time scale of the object. So we create this fake microlensing event divided in different time scales, because of course, as I mentioned before, if we are not observing every day, we are not going to discover many short time scale events. But if we are observing during 5 years, we are going to discover very long time scale events. So the efficiency will depend on the time scale. And then we have the efficiency in the y-axis. So what we see here, this is specifically for microlensing event and specifically for the galactic center. So we see here that the BBB is really good detecting long time scale events, let's say 200 days, for example. And it's really, really low detecting a very short timescale event, let's say planets, okay? Free floating planets or even bounded planets is really difficult for us to detect them. So what we do then to analyze the whole population is to correct by this efficiency analysis, and then we obtain the final sample or the final results, okay? So now that I just mentioned the whole, like the results, the correction and everything, maybe we can go to the animation that I wanted to show. Okay. That is also part of this article. So this is very nice, the fact that we can, right, include an animation in APJ now is pretty cool.
All right, and I'll roll the movie.
Yes. So this is the animation that is included in the article, and it's basically a summary of all the things that I told you now already. So it's showing basically the final result, the 630 microlensing events that we found. And we can see in the upper panel a real image of the area that I analyzed. And in the lower panel, the time, the baseline, the time of the VVV survey, and the magnification of the light curves. And the nice thing is that you can see the location of the different microlensing events. Very cool. And the lights, they pop up, they are showing when the microlensing event happened. And also the magnification of the event is related to how bright is the event itself. So what we see from here, like everything that I explained already can be, inferred from here, because you can see that most of the events occur near the center, and also we have some moments that we don't have any microlensing event, and at some moment we have many of them. So this is also related to the efficiency, as I mentioned, and also it's related to the fact that we have a higher density of stars in the galactic center. So that's why all the events are more concentrated in the center. So this is the result. So we can then go back if you want to the.
Oh, I gotta look at the fireflies going off. It's fantastic. That is just.
Yeah, no, it's very, very nice. So this is basically what we expect to see. Of course, is exaggerated, but it's really nice to understand what we discovered here. So it's the first time we're discovering microlensing events here.
That's a great.
I like it. If we compare, actually, I tried to do a cross match with the discovered microlensing events so far. And we didn't find any of them that were discovered before. So all of them, they are completely new. And this is quite scary because, of course, I wanted to check somehow if all the parameters were, But now in the next stage, like we could do it. So basically what we found is this final sample, and we corrected this final sample by this efficiency. Right. So the final step, I think I'm in almost the last part of the article. So the final step is to first to study the timescale distribution. That is a little bit up. That is just the last one. I mean the previous one.
Yep.
So the timescale distribution is basically a histogram of the timescale of all the events that we found, but also corrected by this efficiency. And the interesting thing that we found is that if we divide the timescale distribution in different beams of longitude, we find that the mean timescale changed as we approach to the center. And this is pretty cool because it's telling us some information about the different stellar populations that are located in different areas of the galaxy. So we start to see some features about galactic structure. So this is really nice. As you can see there, we don't have so many events to be 100% sure about the numbers, but at least we see a very clear trend on these different, mean time scale that we found.
And there's some symmetry above the plane, so that's kind of reassuring.
Yes, no, it's really nice because everything is related. So in microlensing, although it's very difficult to study the lens itself, we can see some very interesting trends. And that's why I'm mixing microlensing with RLiDAS. So I can try to use both, you know, to get like more information about the galaxy. So if we go down, the last part of the article is talking a little bit about the future. So the W1st, that now they changed the name, but now the name is the Nancy Grace Roman Space Telescope. That is the next telescope that NASA will launch. It's going to be a space telescope that will search for microlensing events. And actually it's an infrared telescope as well. So the interesting thing is that with this study, we can help to plan the observation of W1st to try to maximize the amount of microlensing events that we are going to find. So now we are able to study the population of microlensing events. And now with the W1st, we can try to change and to observe a little bit more towards the center, where in the past we didn't know how was to discover microlensing events there. So this is something that we are really waiting for, is a very important part of the W1st will be for specifically for microlensing, for planets, of course, because the cadence is going to be pretty high. Yeah. But this is very, like, this is the first, you know, step. So now we can, you know, have an idea at least. And the last part is to, I use also the proper motions that we have. So this, the plot that you are looking at here is the vector point diagram of the proper motion of the events that we find. And I don't know if you see two structures that are just one next to the other. So you don't see like a very, I don't know if you see it. Well, I see it because, well, you can say no, but the point is that if we plot all the stars that we analyze, you see two structures that are the component of the bulge and the component of the disk, because these proper motion were obtained using the red clamps of the bulge. So we expect the bulge to be in the very center, and the disk to be a little bit, you know, shifted. Yes. So, so I didn't include the background stars here. I just include the microlensing event, but this is something that is telling us where they can be located more or less. I just use them to, you know, to just double check, like, where are all of these microlensing located, to see if there are some very interesting events. And actually we published some other articles using the proper motions, but this is just for completeness, just to show that most of them are probably located in the galactic bulge, like according to the color magnitude diagram and according to the vector point diagram. So, and now of course we are improving the proper motions because VVV is observing for 5 more years. So I think this plot is going to be very improved in the next months. So this is more or less everything. Then of course I compare with other microlensing experiments, but of course we cannot compare directly the surveys because they are completely different. They are observing different band passes. So I just mentioned a little bit what's the difference or similarities, or why VVV can be useful for the microlensing search, and why, for example, some optical surveys are very good, like they complement each other very well. So basically that's it. I don't know if it was clear. If you have any question about it, it's pretty long, but it's a very nice one, I think.
It's an awesome piece of work. And I just want to pick up on the thread that you mentioned that, yeah, there's a series of these articles. And I chose this one because, well, it was the best in the Forsaken. About the best in the Forsaken. And so the other ones, the other articles go into more depth on particular points that I think you raised. So there's this gorgeous series that people can take a look at. And
there are other articles talking about the different structures, like analyzing a little bit more the events that we found, and also For example, we then search for a piece of like the latitude dependence as well. So we extended a bit the area just to do a superposition with the other surveys to double check. And we found very nice structures. And the last one that we published is about the far disk events. So DVV is detecting, because it's a 4-meter telescope, is detecting some stars in the far disk, like beyond the bulge. And we have some very nice candidates of this sample that are with sources in the far disk, let's say. So everything is different because even the transverse velocities, the relative distances, and everything is completely different. So this is a very new area of microlensing that, of course, is going to be improved with the Nancy Grace Roman Space Telescopes and the new telescopes that are coming now.
And of course, VVV is still running, so you know, there'll be another 5 years worth of data.
Actually, yes, we are lucky because the VVVX is the extension, and it was supposed to end last year. But now the spectrograph that will be in the Vista telescope instead of the detector that we have so far is delayed. So we are still running just because we are delayed with the spectrograph. So we don't complain at all. And we are still, you know, trying to get some nice results. Yes.
Very cool. Very cool. Well, Gabriela, Dr. Navarro, I want to thank you so much for spending some time with us and walking us through your really lovely article. And I look forward to some really cool results from VVX in the future. So thank you.
Yeah. Thank you, Frank. Thank you for inviting me. And this is a really nice idea that you are doing this video. So yeah.
Yeah, I think it's good to associate the person with the paper, so you get to see what they're like and how they present. It's more than just a name on the paper. They're real people, and they have a story. So it's all.
Yeah, that's true. Thank you very much for this.
You're welcome. And goodbye, everyone, and we'll see you on the next one. Bye-bye.